Hi everybody, Denny here from Cold Quanta. Welcome to 3 Minutes of Quantum Computing. Today we're going to program the Star Battle Cubo in Python. In order to make this simple, I'm going to use the SymPy package. Using SymPy, you can create variables, make expressions using those variables, and evaluate those expressions, plus many other things. We'll use SymPy to help automate building our cubos. Here's the makeCubo function. It takes a single argument, which is a text string defining the puzzle. Each region is assigned a letter, starting with A, and the string of letters corresponds to reading across the cells of the grid starting with the first row. makeCubo's first step is to find the length of the puzzle string and take its square root to determine the grid size. Then we loop over grid cells, and for each one we create a SymPy variable and put it into a dictionary keyed by row-column pairs. varname is a simple helper function which converts row-column tuples into a string name variable. makeCubo is now ready to build the cubo. This first section creates subcubos for row constraints, column constraints, and region constraints. Each subcubo is built by a helper function, and the resulting expression is accumulated into the cubo variable. Here are the helper functions. They build subcubos one constraint at a time. The cubo for row constraint function takes the grid size, variable dictionary, and row number as its arguments. It uses a list constructor and vardict to build a list of the variables appearing in the row. The final statement forms the sum of the variables, subtracts 1, and squares the expression before returning it to the calling function. Here's the value the function returns for the first row of the grid. Now we need to handle the neighbor constraints. That happens in this section of code. The outer loop iterates over all grid cells. The 4 if statements correspond to the horizontal, vertical, and 2 types of diagonal neighbors. The if statements keep our indexing arithmetic from falling off the edge of the grid. We don't use helper functions because the subcubo that we need to generate is simply the product of 2 variables. The result of all this work is a SymPy expression which holds our cubo. Here it is, 64 variables with a total of 8 row constraints, 8 column constraints, 8 region constraints, and a large number of neighbor constraints. The last step of our function converts the SymPy cubo to a NumPy matrix. This is how the conversion proceeds for a 3-variable cubo which converts to a 3x3 array. The blank entries in the array are all 0. The summation expression shows how the array gives us a handy way to write the cubo as a double summation with subscripted variables. A word of caution. Different programming APIs have different conventions about how to handle the off-diagonal matrix elements. After the conversion, our cubo is a 64 by 64 element NumPy array. Here we are scrolling down across the rows and then across the columns. The pattern of entries captures all the constraints of the puzzle. Now we converted Star Battle into a cubo and encoded the cubo as a NumPy matrix. The next step is to simulate our cubo to make sure that our conversion process is correct. That's it for today. Thanks for watching. Bye everybody.